Hi everybody, this is a video recording for Math 211, Elements of Geometry for Hartford Community College, and this is Chapter 1, Section 1-2. So Section 2, the first section we're going to look at in our geometry textbook. In Section 1-2, we're going to start taking a look at geometry, define what geometry is, look at some logic, and then look at different patterns, how to predict patterns, and then different parts of a mathematical system, and then also some assumptions that we can or cannot make in geometry. All right, so just to start off with the basics, geometry is a word that comes from the Greek language, and it means to measure the earth. So kind of cool to know. Not something I'm not going to test you on, but if you're teaching and you have kids, they might ask you, what does geometry mean? So it means to measure the earth. And geometry is all about logic and reasoning skills. And a main part of geometry is really being able to explain your steps, using logic to explain why do the three angles in a triangle equal 180? Why do corresponding angles in parallel lines, why do they have the same measure? So using logic to do this, to recognize patterns, make conjectures, which are also like hypotheses, and also develop the laws of the system, the rules of the system. So we're going to talk all about that in this section. All right, so we're going to start off and we're just going to use a little logic and we're going to look at patterns. So the first pattern we're going to look at here, we have these three squares or rectangles. Really can't call them squares yet, but we know they're rectangles. And they also seem to have, some shading. This one, it's in the upper left-hand corner. And the second one, it's in the upper right-hand corner. And then the third one, the shading is in the lower right-hand corner. So for the fourth rectangle in this pattern, where will the shading be? I'm going to draw the rectangle. All right, so take a second. Where will it go? And if you said the lower left-hand corner, you are correct. It would be shaded there. And we used logic. We looked at the examples that we had and followed those to find the fourth iteration of the pattern. Okay, so now we're going to look for a pattern and predict the next number in the pattern. So for our first one, when I look at patterns and I look at number patterns, the first thing I always do is I look at my numbers and I look to see, are they increasing or are they decreasing? And if you notice in this pattern, all of our numbers are getting bigger as we move from the left to the right. So we have 2, 10, 50, 250. So really what I want to do is when I think of numbers increasing, you want to think of certain operations. And when I say operations, addition, subtraction, multiplication, and division, I'm going to think of operations like addition and multiplication. Those are going to give me increasing numbers. So I always start with addition because it's the easiest and we tend to like addition the best. But if I go from 2 to 10, if I do addition, I'm going to add 8. Okay. Now, if I go from 10 to 50, I'm not adding 8, I'm adding 40. And then if I go to 50 to 200 or 250, I'm adding 200. So I really don't see too much of a pattern there with addition. So now, instead of addition, let's take a look at multiplication. All right, well, I know if I do 2 times 5, I'm going to get 10. If I do 10 times 5, it gives me 50. If I do 50 times 5, it gives me 250. So now, if we do 5 times 250, or 250 times 5, we are going to end up with 1,250, and that would be the next number in the pattern. So here is the pattern that I determined. It's increasing, or it's being multiplied by 5 each time. And your patterns aren't always going to be the same. Like you might come up with a pattern and someone else may find something different. As long as you can explain it and it works logically for the next number in the pattern, it works. It's okay. All right, let's take a look at B. So for this one, again, our numbers are increasing. We're going from -3 to 0, 0 to 3, 3 to 6, and 3 to 9. So again, I tend to start with addition. I know to go from -3 to 0, I have to add 3. From 0 to 3, I have to add 3 there too. 3 to 6, we're adding another 3, and 6 to 9, we're adding 3. So my pattern here is they're adding 3 each time. So that means my next number will be 9 plus 3, or it will give us 12. All right, so we started looking at some logic skills. What we're going to do now is use our logic and reasoning to develop the mathematical system of geometry. Geometry, that's what we're studying in this course obviously, is a mathematical system, and all mathematical systems consist of undefined terms, defined terms, postulates or axioms, and theorems. And really, what I would like you guys to do during this course is I want you to take notes on each of these PowerPoints and presentations. But in your notebook, I would like you to, and if you want to do it at the back or the front, it's okay. I want you to have, you really only need maybe 1 or 2 pages for undefined terms. I want you to have a section for undefined terms. I want you to have a section for defined terms, a section for postulates or axioms, and then a section for theorems. Your defined terms, postulates and axioms and theorems will obviously be bigger than undefined terms. Postulates and axioms will be pretty big. So I would leave, 6 or 7, maybe 8 pages for each of those. And if you make a list of those, that will be very helpful whenever you're studying or you're doing a proof to go back and look for information. You have them all listed instead of scattered throughout your notes. You have your undefined terms first, then your defined terms, postulates, and you can just flip right to them and look at them. So that would be a great way to organize your notebook. And we mentioned on the last slide that the mathematical system is made up of 4 parts. We have undefined terms as our first part. And your undefined terms are the most basic terms that we do not formally define, but we have a meaning or description that we agree upon. So that it's kind of difficult to think of undefined terms as undefined because they're terms that we think of, we have a definition for. We're going to talk about those in the next section, some undefined terms, but some examples of those would be like a point in geometry. It's considered an undefined term. A line. So how we define a line is really undefined. A plane. Those are just some examples of some undefined terms that we will talk about. All right, we will have definitions, formal definitions, where we use undefined terms or already defined terms to formally define them. And we will talk a little bit in Chapter 2 about what makes a good definition and how do we know it's a good definition. We also have postulates or axioms, as they can be called, and those are statements that we accept as true, but we don't try to prove them. So we don't maybe do a formal proof to prove them. One postulate that I can think of right now, and we'll talk about it quite a bit, is our segment addition postulate. That's one of the first ones we'll look at. And then our final type of or part of a system are theorems. And theorems are statements that we prove using logic. The foundation above, so we use postulates, definitions, or undefined terms, or any other previous theorems. So theorems, we can prove it's true. We write a formal proof for it. One of our famous theorems that you guys probably have worked with before would be like the Pythagorean theorem. And we'll look at lots of different theorems during the course of this geometry class. Okay, so the last part of this section, we're going to talk about figure assumptions. In geometry, and in any class, really, sometimes you look at pictures, we make assumptions, but unless we have information or evidence to back up that, we can't always assume. that a figure is what it looks like. We have to have information to back it up. So, and this happens a lot in geometry, we have unmarked figures, and we have to be careful before we assume anything. And you'll see this when we do proofs. You'll look at things and you'll assume, oh, this is, a parallelogram because it looks like a parallelogram. But if it doesn't have anything marked, if it doesn't show the opposite angles are congruent or both pairs of opposite sides are parallel, it can't be called a parallelogram. Even though it looks like it, we need to have that information. So here they're giving us a bunch of examples, and they're going to ask us, can you assume? So the first one, can we assume that this right here is a line? The answer to that, I want you to think in your head, yes or no. Okay. The answer is yes, and we can assume it's a line because a line is something that goes on infinitely. And to show that, they put these arrows on either side, and it's a straight shape. It doesn't have any bends or curves to it. It doesn't have any vertexes where it might bend to be an angle. So yes, we can assume this is a line. For the second one, can we assume that this is a right angle and it measures 90 degrees? If I look at this, it definitely looks like a 90-degree angle to me. What do you think? Yes or no? Okay, if you said no, you are correct, because even though it looks like it's 90 degrees, we're missing one key element to show that it is 90 degrees. If it's a 90-degree angle, they will either tell it to us, give us the information, or they will put that symbol in there. Otherwise, if that symbol isn't there, it could be 90.5 degrees, which does not make it a right angle anymore. It is not 90 degrees. So again, you have to make sure the marking is there. Okay, so now we have 4 more to look at. So for this one, can we assume that this is a right angle? If you look at this one here, hopefully everybody in here or listening should be shouting yes. And the reason being because it has the marking that I put on the last one. So yes, that is a right angle. We can assume that because we have the marking there. All right, can we assume that these angles are supplementary? And it means when they're supplementary, that they equal a sum of 180. Now, when you look at this shape right here, right now there are no markings on here, so you may not be sure. But the answer to this is, can we assume that they are supplementary? The answer is yes. And the reason being, right here, notice what shape is this that we've already talked about? It is a line. And if you know from previous experience, a line always measures 180. So because these two angles are made up of a line on the bottom, they are supplementary, so we can assume that. And we will do a lot with supplementary angles, or linear pairs, as they can also be called sometimes, during the course of this class. All right, our next one. Can we assume that these angles have a common side? So if we look at this figure right here, a common side means they share a side. If you notice right here, here's the first angle, here's the second angle, and I did highlight this side right here twice. That is their common side. So yes, they do have a common side. All right, and our last one. Can we assume that these two lines intersect to form angles? Well, if we look, all right, there are two lines. Sorry, my pen doesn't allow me to draw straight very much. But they do intersect right here. And they do form angles. So we got angle here, angle here. We also have like an angle here, an angle here. So yes, we can assume that. Okay, and we're continuing with our figure assumptions. And here, for our next one, they want to know, can we assume that these angles are complementary? So they add to a sum of 90. So here, unlike the supplementary, we don't have a straight line, so we can't tell by that. But if I look at these two, again, this really looks like a right angle to me. So can we assume that these two angles add up to 90 degrees? What do you think, yes or no? Okay, if you said no, good, because if you look, we're missing that key point there. It still needs to have that marking between the lines to show that they're complementary. So you can't assume unless that marking's there or they tell you that the two angles are complementary. All right, and then for this next one, can we assume that these segments have equal length? So if I'm just looking at these, they look pretty equal to me. So what do you think? Yes or no? If you said no, that's good. Although they appear to be equal length, we can't be sure unless they have markings or they tell us the measurement. So right now, this one could be 2 centimeters. That's a very bad 2, sorry. So 2 centimeters, and this one could be 2.1 centimeters. So just slightly bigger. We don't know because we don't see the markings. So we do have to assume that they are not the same unless they give us information otherwise. Okay, so for our next one, look at these two. So they're similar to the last one. Here, can we assume that these angles are complementary, a sum of 90? Hopefully I hear lots of yeses because, again, you got that 90-degree symbol there. So yes, we can assume they're complementary. And here, can we assume that these segments have equal length? Notice they're both marked at 1 inch. So because they're both marked with the same measurement, yes, we can assume that they have equal length. Another way that they tend to mark segments, we can just put like a slash through them if they both have 1 slash. That also indicates that they are equal length. They don't have to have numbers necessarily. Okay, our last thing that we're going to look at here is, given this figure, can we assume that this is a square? When I look at this, it looks very much like a square to me. So in the beginning, I would probably say, yes, this is definitely a square. But with geometry, again, you have to be able to back it up. You have to have the information. So what do you think? What do you know about squares? I want you to think about it. What do you know about squares? And is this a square? Okay, so when you thought about a square, hopefully you said, well, I know a square has all 4 sides that have equal length, and then all 4 angles are right angles. If you look at this figure, it definitely looks like, excuse me, definitely looks like a square, but they did not mark all 4 sides the same and all 4 angles. So they didn't mark 4 right angles. So if you look down here, in order for us to say it's a square, we need to have all 4 sides marked the same and then all 4 angles to be right angles for us to definitively say, yes, it is a square. So it's hard to get used to because we're just used to taking things for face value, but really what you have to do is you have to be able to back it up. You have to have the information to back it up. And that's what we're going to work on throughout the class with our geometry. And this is it for section 1-2. So hopefully you took some good notes, and we will move on. The next video will be on section 1-3.